Here's a second video of Chapter 6 dealing with fictitious forces. You may say, well, physics is hard enough with the real forces. Why do we have to deal with fictitious forces? Good question. Well, what happens if you're in a non-inertial accelerated frame of reference? That's what we're considering. In an accelerated frame of reference, non-inertial, we must introduce fictitious forces to explain motion. With these fictitious forces, we can then use Newton's laws to explain what happens. Otherwise, we can't, and we'll see why in a moment. Examples of fictitious forces are the Centrifugal Force and the Coriolis Force. Imagine this. Let's say you're in a boxcar and you can't really see outside, and this boxcar is moving along, say at 50 miles per hour, and you look at a pendulum and you notice that as it's moving along at 50 miles per hour, that pendulum is straight up and down, and there's no problem with that. The net force on it is zero, it's not accelerating, and in your frame of reference, it's not accelerating. In the frame of reference of somebody outside the boxcar, if they happen to see in through a little window or something, they would notice the same thing, that it was not accelerating. Okay, good enough. But what happens if the boxcar all of a sudden starts to increase in speed? So it starts to accelerate. So as a result of that, it moves off to the side like this. So the boxcar is pulling along, and if you were an observer outside the boxcar, and if you were able to see this, you would say, oh yeah, that makes sense. The train is moving along and it's pulling, and the tension of the cord is what's pulling this mass along and allowing it to maintain itself with the train. All right. Well, let's say you're inside the boxcar and you're looking at this, and you kind of look at this and you say, well, from my perspective, this cord and this ball are stationary. So, I mean, they're really not moving, and they're kind of off to the side like this. And I know that there's tension in this cord, and it's going like this. And I know that there's gravity going down towards the center of the Earth, mg. But why is this stationary? Because there's a component of tension that's going this way. What is the force that is offsetting that component of tension such that this is stationary as I'm looking at it? And that is a good question, because physically there's really no real force that is offsetting tension, allowing this to stay stationary as you see it. So we have a dilemma here. The inertial observer would see the ball accelerated. Newton's second law applies to the ball. The inertial observer is somebody who is outside on firm ground. And they would say that the reason that this ball is being accelerated is because the component of tension along that direction, in this case t sine theta, theta being your angle from vertical here, is supplying the force, mass times acceleration, that is accelerating the ball. If you're inside the boxcar, though, you have to make up a force which you call mass times acceleration, that is going to offset the tension force component such that this ball remains stationary. So based on that, you apply Newton's first law, that for a stationary object, and you would have that this t sine theta that's going this way is being offset by mass times acceleration this way, ma, and that's why this ball is stationary as you see it. Based on that, you would say in either frame that t sine theta is equal to mass times acceleration, and you would say t cosine theta is equal to mg. So you would have tangent of theta is equal to acceleration divided by g, or your acceleration is equal to g tangent theta. Now, in one frame, you're making up a force, mass times acceleration. In the other frame, mass times acceleration is already determined by the acceleration of the boxcar. In either frame, the acceleration we're talking about is equal to g times the tangent of this angle theta from the vertical. The reason you have to make up a force when you're in the boxcar is because your frame of reference itself is being accelerated. When you're in an accelerated frame of reference, weird things can happen. And if we want to use Newton's laws, which we do, then we're going to have to make up forces to account for the fact that our frame of reference itself is being accelerated. In this case, the force we had to make up was this ma going in the opposite direction. But we have to do that for any frame of reference that is non-inertial, any frame of reference that itself is being accelerated. We have to make up forces in order to make everything balance. So if we had this situation where we had a boxcar and we had a pendulum at a 45-degree angle, what would be the acceleration of the boxcar in that sense? Well, we can actually use that data to measure that. The acceleration would be g tangent theta, 9.8 times the tangent of 45 degrees. And the tangent of 45 degrees actually is 1. So in that case, our acceleration would be equal to g, 9.8 meters per second squared. So if you were driving a car and this went off at an angle of 45 degrees, then you are accelerating your car at 9.8 meters per second squared. Consider this. Say you're in a car approaching a curved exit ramp, and let's say you've slicked down the passenger seat. You're on a date. You're trying to impress. You're trying to do everything you can to be good on your date. But then you thought, it'd be nice to conduct a scientific experiment at the same time. So before you go on the date, you slick down the passenger seat so that there'd be no friction there. And you decide, as part of your experiment, you're going to paint all your windows so that you can't see outside. You're going to just rely on your navigator to help you steer the car. So as you approach a curved exit, you reach this curved exit, and you start going around it, and the navigator's helping you out. But you notice from your perspective that your passenger is starting to slide toward the outer door. If you had another observer looking down through your sunroof, they would observe that the car and you are going in circular motion, and you're obeying Newton's laws according to that there's a centrifugal force on the car, and there's a centrifugal force on you, which is the friction of the seat, and those forces are allowing you to maintain that circular motion. But they would also observe that your passenger was going in straight line motion because there is no net force on her. She is continuing along in a straight line, and so as the car is going around the circle, she continues in a straight line, and hence she hits the outside door of the car. So she is under Newton's first law, which says if there's no net force, you proceed in a straight line. So there's no problem in an inertial frame of reference describing what's going on. But if your frame of reference is inside the car, and you're looking at your passenger and she's sliding out towards the door, what do you say? Are you feeling okay? Yeah, there's some special forces acting on you today, and you would have to conclude, yes, there is a fictitious force acting on your passenger. And so we have to make up a force to explain what is happening to her in your special frame of reference. The force that we make up is called the centrifugal force. An inertial observer observes Newton's first law. Body is continuing in a straight line, but a non-inertial observer in the car creates a fictitious force to explain this motion, and that fictitious force is the centrifugal force, and that explains the motion of the passenger sliding out towards the outer door. The magnitude of that centrifugal force is equal to the magnitude of the centripetal force that would have been required to keep the passenger moving in a circular motion along with the frame of reference. So they have the same magnitude, but the centrifugal force is pushing outward from my perspective inside the car. Here's another example of a centrifugal force. Say you had a mass sitting on a turntable. Turntable is one of those old devices that used to move things that we called records to play music. So a turntable is going around. We put an object on it, and what's keeping it moving around on that turntable would be static friction. So static friction is supplying the tension or the friction that will allow it to maintain itself on the turntable. So you would say that your centripetal force is that static friction, or designated by T in this case, that is allowing this block to stay on the turntable. But if you were a non-inertial observer and you were on the turntable itself, then you would have to wonder why this block is staying on this turntable. What is keeping it? Because from your perspective, it should fly off. So there is a force that is offsetting the frictional force going inward on this turntable, and that force is equal to mass times velocity squared over r, and that is maintaining this block as being stationary on the turntable. So you have to make up this force, and this force is equal to that centripetal force that was required to an inertial observer that kept the block moving in a circle. So the centrifugal force is equal in magnitude to the centripetal force required in an inertial frame, centrifugal force in a non-inertial frame. Here's another example. Say you're on the Earth, and because by virtue of being on the Earth, let's say you're at the equator rotates around once a day, and the circumference of the equator is 25,000 miles. So over the course of one day, 24 hours, you move 25,000 miles. So if you were at the equator of the Earth, you would be traveling at a speed, just due to the Earth's rotation, greater than 1,000 miles per hour. However, if you're at the North Pole, you're just kind of moving around like this, and so over the course of a day, you really have no velocity. So a person at the equator is moving at 1,000 miles per hour. The person at the North Pole is stationary, basically. So if you were to set up a missile and you were to shoot it from the North Pole, aimed at some point on the equator, if you aim right at that point and you shot your missile, over the course of time while it's in flight, the Earth would rotate. And that missile would hit to the west of where you aimed. From your perspective, if you're at the North Pole, that's perfectly natural. You're in a non-inertial frame, you're not really moving, you're not rotating, and you would see that you shot and the Earth spin underneath it and you hit to the west. Fine. Now what happens if you were on the spinning Earth? Let's say you were at the equator and you saw this missile shot right at you, and as it was coming at you, it veered off to the west and missed you. How do you explain that? Well, you would explain it, you would have to make up a force to explain the fact that this missile veered off to the west. And the force you use to explain this is called the Coriolis Force. The Coriolis Force accounts for the Earth's rotation because we are in a non-inertial frame of reference. We are on a rotating Earth, which itself is accelerating because we're on this circle of the Earth and we go around in a certain amount of time. We have a centripetal acceleration. Our frame of reference is under an acceleration. Hence, our frame of reference being on the surface of the Earth at any particular latitude means that we have to make up forces to account for what happens in our everyday life. And one of those forces is the Coriolis Force. It happens to be proportional to the angular velocity of the Earth squared. But it's something we apply to a lot of things. If you had a storm brewing in the Atlantic over some expanse of latitude, the latitude that's closest to the equator is moving faster than the latitude that is at a higher latitude, and that's going to cause a rotation in the storm that goes counterclockwise. So all your hurricanes that develop in the northern hemisphere have a counterclockwise rotation. In fact, all your major storms will be counterclockwise in the northern hemisphere. If you're in the southern hemisphere, it'll be clockwise. So your typhoons that develop in the southern hemisphere are all clockwise. 99% of the tornadoes that develop in the northern hemisphere are counterclockwise rotation. 99% of them. So 99% of the tornadoes that you might see, counterclockwise rotation. 1% clockwise rotation. That 1% might be more influenced by, say, the jet stream airflow than say, the expanse over a latitude of the development of that storm. But 99% of them are indeed counterclockwise. Some people use the Coriolis force to try to explain the rotation that a commode would rotate when you flush it. But the expanse difference in latitude on the different ends of a commode is not great enough for that to be a significant factor for the flushing direction. It turns out that most northern hemisphere commodes will rotate in a counterclockwise direction, but it's probably due more to the mechanical design of the commode than due to the Coriolis force. But it's something to test out. So that's a short explanation on fictitious forces and why we need them, because we have non-inertial frames of reference. And if we want to use Newton's wonderful laws of motion, then we have to make up these forces in order to balance things so that we can still use Newton's laws.